We saw previously that simply eyeballing the straight line fit to the data wasn't really satisfactory, and that somehow we needed to be able to quantify the goodness of fit of our straight line. We also saw that in some very simple and crude way that taking the mean of a data set can be thought of as a very simple model. If we do that, which we've done here in figure A, we see that we have a set of data points. The straight line here represents the mean value, and we'll see that there is a distribution of errors that's usually going to be quite broad when we fit the mean. So there's a lot of scatter about that mean value. We also looked at how to fit a straight line to this data. And so we can see that the difference between the straight line and the data points appears to be smaller in this case. So the errors in this case, we might expect to have a distribution that is a little bit tighter than the distribution that we got for the case of the mean. The question we need to ask ourselves, though, is this linear model, the model that we fitted in curve B, really any better than just using the mean value? And if it is, what's the improvement? Can we try and quantify it in some way? We also saw that when fitting a straight line to a set of data points, there's an error between the data and the fitted line. For the ith point, we define the error, EI, as being yi, which is the data point, minus a0 plus a1xi, which is just the equivalent value on the straight line. So that's the difference here represented by the red arrow in the figure. It's the distance between that point and the green point at the top there. An estimate then of the total error, that is over all of the data points, is the sum of the square of the errors. So SR is equal to the sum of these EI squareds, which just equals the sum of yi minus a0 minus a1xi all squared. And recall that this sum of the residuals, this SR, is what we minimize to find a0 and a1. We can do a similar thing now, except instead of using the straight line fit, use the mean value. So we can define the difference between the mean value, which is y bar, and each of the data points, yi, and square them, then sum them up to define this quantity which we're going to call st. So st is the sum from I equals 1 to n, yi minus y bar squared. This is looking very similar to the variance. We just needed to divide this by n minus 1 to get the variance. Now we're going to define the coefficient of determination, r squared. And we define that as being equal to st, which is a deviation, some of the deviations from the mean value, minus sr divided by st. That's just a definition. It is something that you need to remember. So let's have a look at what kinds of different behavior we can get. So defining r squared, again, remembering what SR is equal to that sum of squares and ST is equal to that sum of squares. If we have a straight line and all the data points actually sit on top of that straight line, then r squared is equal to 1. That's because SR is equal to 0. So if we look at this term here, if the data points sit on the straight line, then we know that yi is going to be equal to a0 plus a1xi. So SR 0, r squared is 1. It's a perfect fit. So r squared equals 1 means all the data points are on the line that you're trying to fit to. If, however, SR is equal to ST, then r squared is going to be 0 because the top line up here is going to be 0. And this is an example of the case where the mean value is represented by this line here and some kind of straight line fit is represented by that line there. The sum of the errors between those two different lines is the same for both cases. So basically what this means is choosing this particular straight line up here, there's no improvement over the mean. And it is possible that SR can be bigger than ST. And in that case, then r squared is less than 0. In other words, the linear fit is worse than the mean. Now, it's not possible in an unconstrained linear regression to actually get this case where r squared is less than 0. And in actual fact, it's generally not possible to get the case where r squared is equal to 0 either. R squared will nearly always be greater than 0, somewhere between 0 and 1. So then what does r squared represent? So let's go back to our force versus velocity data. And if we go through the process of calculating the coefficient of variation for this particular curve fit, we can show that r squared is equal to 0.8804 to 4 significant places. What this indicates, what this is telling us, is that 88.04% of the deviation of the data from the mean value is explained by the linear model that we fitted. There's another approximately 12% that isn't explained by the linear model and actually arises from some other cause. So it's giving us an indication of how much better the straight line fit is to simply using the mean. Just like we defined a standard deviation, Sy, at the set of data points, which is just equal to the sum of the square of the residuals divided by n minus 1, take the square root of that entire thing, we can also define a standard error of our regression. We call that Sy/x, and it's given by this formula here, which is more simply written as the sum of the square of the residuals between the data points and the fitted line divided by n minus 2, taking the square root of that entire thing. Now, don't ask me why n minus 1 here and n minus 2 here. That's buried deep in these statistics. The final thing I wanted to say about error in regression is that one needs to be careful making judgments purely on the basis of the coefficient of determination. So here's 4 examples. They're commonly known as Anscombe's quartet. 4 different cases. In case 1, we have a scattered set of data points which we fitted a straight line to. In case 2, we seem to have what looks like a nice parabolic trajectory, but we fitted a straight line to it. In case 3, we have quite a nice looking straight line and an extra point here. And case 4, we have a whole bunch of data points all at the same x value with an outlier up there. It turns out that if we go through and crunch the numbers, all 4 regressions have the same result. Y is equal to 3 plus 0.5x, and that the coefficient of determination is equal to 0.67. I would argue that some of these curves are actually, some of these data points, are actually reasonably well fitted by this straight line here, and others of them are not. So for example, this is very poorly fitted by that straight line. This is not a good representation of what's going on, because in actual fact, if you'd fitted a parabola, you'd probably be able to fit this data exactly. This is probably okay, and this point here, well, in actual fact, we probably need to be drawing a different straight line and getting rid of that data point up there. So the fundamental take-home point from this is, just because r squared might be close to 1 doesn't mean the fit is a good representation of reality. So fitting a curve, fitting a function to a set of data points is just a guess to what's really happening underneath, and one really needs to look at the physics to see whether what you've fitted is a good representation or not.